Hello everyone. Welcome to the sixth live session of Bigyan Chachar Asor. Bigyan Chachar Asor work to promote knowledge among students. It plays the role of a bridge between professional scientists, university professors, teachers, science enthusiasts, and students. Bigyan Chachar Asor also fight against superstitions and promote scientific temper among students. Today, we have an honorable guest, Devashish Goswami, with us. Devashish Goswami is former group director of ISRO SAC and former project director of National Meteorological Data Reception and Processing Center, New Delhi. He was the he was with ISRO for 30 years, starting 1983, and has major contribution to all India satellite remote sensing camera payloads in various roles as designer, developer, team leader, and reviewer. He has been mentor and guide to a large number of students, trainees, young engineers, and external projects. Devashish Goswami has outstanding contribution towards indigenous satellite payloads for remote sensing, cartography, and metrology. His major research and development areas include electronic subsystems, hardware, and software solutions for satellite electro-optical camera systems, baseband and ground systems, evaluation and test systems, architecture for indigenous computing solutions, and operational meteorological systems. He has mentored, coordinated, and guided Indian industry based space technology projects which are successful and operational. He has received awards like ISRO Prashanshaniya Avang Mahatvapurna Seva Award from Astronomical Society of India Spacecraft and Related Technology Award, from Indian Society of Geometrics National Technology Award, and from ISRO Team Award for EO payload system and related projects. Today, we are really happy to have Devashish Goswami with us. So now I will hand over to Mr. Goswami.
Many thanks, Sabyasachi for the very kind and very generous words describing me. And I thank Bigyan Charcha and Sabyasachi for the opportunity to speak on the space technology and the journey of ISRO since last now 50 years, 50 plus years actually. And I am thankful to all the young people who are joining today and the professors, teachers of science technology. And I also really appreciate the fact that we have such a Bangla Bigyan Charchar group, which is inoculating such scientific temper amongst our young generations and to bring about a better change for the entire country. Thank you so much, Sabyasachi. So I will start with the journey of ISRO. This is actually from the ISRO website itself. The journey starts from way back in 1962 when ISRO was formed as INCOSPAR. So actually the space research was initiated by a very great visionary of our country, Dr. Vikram Sarabhai. He was actually from a very accomplished family of the previous Sarabhai family, which also was part of the Calico group of mills in Ahmedabad. And they still are well known for propagating arts, environment, everything, even though Sarabhaiji himself, Vikram Bhai himself, is gone in 1971-72. So he was the visionary who created the Indian Space Research Program, and with considerable help and guidance from Dr. Homi Bhabha. Initially, this was constituted as the Indian National Committee for Space Research in 1962 under the Department of Atomic Energy in COSPAR, and the actual Indian Space Research Organization was established in 1969 in place of INCOSPAR. Further to that, the Government of India constituted the Space Commission, and what used to be the actual, what we call the Indian Space Research Organization, was created slowly by combining all the such centers into one area under the Department of Space. Okay. So what started as the Thumba Equatorial Launch Station, TERLS, in 1963, on 21st of November 1963 was the first such sounding rocket launch. Initially, the rockets M100 from Russia and France Centaur were brought, and these rocket-based systems created the, what you say, the atmosphere and the environment for the young people of those days, 1960s, to create such a program, which started first with the rocket launching systems and the learning of the solid rockets in this branch. We'll go to the next slide, sir. So Besachi, next slide, sir. The photographs.
This is
No,
okay.
no, 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 not
Okay.
back.
You
Photograph. Yes. Yeah. So these are some of the unique photographs which we have here, and which I have dug out from somewhere. The first photo shows the actual names which are very common now. The photograph sitting on the left side is Professor U.R. Rao, who was the center director, and his center is named after him. The person sitting second on the right side is Dr. Abdul Kalam in his younger days. We have on the center from left sitting is Professor E.V. Chitnis, who is recently one of the only surviving persons. He is 100 years now, and in Pune. And standing third from the right is Dr. Madhavan Nayarji. So these are all the stalwarts who were actually part of the TERLS, and they were the people who led ISRO later on. The second part is the formation of the legendary Earth Station built in 1996 at Ahmedabad. And this was also created, surprisingly, at the insight, I will tell you, that this was created on a land which was owned by Dr. Vikram Sarabhai. He donated it for the nation. And this was started as the ESCAS, Earth Station for Satellite Communication and Learning Process. The third photo is the church, which is still preserved as a museum. This is where the Thumba rocket launching site was there, and it is preserved as a museum at Trivandrum. You can go to the next slide, sir. Yeah. So here the experimental satellite communication station located in Ahmedabad was operationalized in 1967. This is an important milestone, which generally is an insight which a person like me will be able to give. It does not come out in the general parlance. And this started what is called the satellite communication systems in India. All the television channels of India today work on INSAT satellite systems, and many other satellite communication systems have been established by ISRO for a lot of other agencies of India. To establish, ISRO had a clear need not to wait for. So as a result, a program was started for Krishi Darshan using the terrestrial transmission, and then we went over to create the SITE program. SITE program was very famous. It is the world-class famous, and it's also there in the Guinness Book of World Records, actually. We can go to the next slide here. Yeah. So SITE program is also very famous, SITE. This was actually what is called a satellite instructional television experiment, hailed as the largest sociological experiment in the world. And people from all across India, 2,400 villages, we made use of the United States, USA, American. It's actually the advanced technology satellite called from the USA. They had loaned it to us for almost 18 months. And the 6.1 meter antennas were used. There is another insight I will give. Recently, we had a lot of talk about the unfurling of the antenna of NISAR. But way back in 1975-74, the ATS Satellite 6 had one of the largest unfurlable antennas, of course, for SATCOM. So it's there. So it's very old technology, I will say, which was successfully operated. And this program was specially made for training the village people as well as by communicating science and technology across India. Following this was the Satellite Technology Experiments Program, the joint product with Post and Services. And this was for giving out similarly what we call domestic communications, enhanced capability and experience. And these were the first what we call the first steps of the ladder with which the use of space technology for societal good, which was the original vision and still is the vision of ISRO, that it is use of space technology for societal good, was actually carried out. You can go to the next one. Then comes the phase of 1975-76, where we created the first satellite called Aryabhata. So named after our famous mathematician of uh, third, fourth, fifth century, when he is actually was there. So this was actually created and it was launched using a Soviet launcher. So this was our first test satellite, and it was indigenously developed using indigenous equipments as much as we could in the way back in the 70s. This was followed during this time historically or as a landmark. We are going one by one. The satellite launch vehicle 3 called the SLV-3, which could place a 40 kg low Earth orbit satellite, which was first successful flight was done in 1980. And through this program, competence was built up overall design for design, vehicle design, mission design, material, hardware fabrication, solid propulsion technology, control power plants, avionics, vehicle integration, checkout, launch operation, development of multi-stage systems with appropriate control and guidance systems to orbit a satellite was a major landmark in our space program, which started initially in 1980s. And we can go to the next slide where we go to ASLV. Yeah. So in the experimental phase during 80s, an end-to-end capability demonstration was done and associated ground systems. So space technology is not just about what is called the rocket part of it. Along with the rocket, we have the satellite, and along with the satellite, we have the payload. So afterwards, I will explain this linkages as well. So along with this, what came the associated ground systems which are needed for users. So if we have a camera put on a satellite and then we need to receive the data, along with receiving the data, we need to have somebody to use the data. So that is the entire ground system. If we have a satellite communication system, we send up the satellite, we need a upload station, let us say a television or a communication system or a voice message system. And this system in turn uploads to the satellite, which redistributes the data in its reflector and re-powered mode from the geostationary orbit back to all the centers of India. And there, through the dish antenna systems, we again have what is called the baseband systems, through which we decode those signals. And after decoding them, we actually put them back to actual use, either voice message or teletype or text messages or television transmission in what we know as the MPEG formats. In this time, there was the what we call the Apple program. Now, the Ariane passenger payload. Ariane was a launch vehicle from France. Today, it is called the Ariane company hai, Pura. And this, they were creating their first test rocket actually. So whenever a person creates a first test rocket, whether it is India or NASA or France, they wanted somebody to test their satellite on it. So we were given a free launch from the Guyana, their launch pad. And this entire satellite, Ariane passenger payload experiment, that was made at within ISRO. And this was our actually the first future communication satellite. So the basic construction of a satellite bus for satellite communication started with this. At the same time, because ISRO is not working only on satellites, only on rockets, simultaneously several other centers were working. So the augmented satellite launch vehicle was demonstrated. This augmented satellite launch vehicle, along with the satellite SLV earlier, it would have strap-on systems, which is the way we go around now. And this paved the way. This also included what is called the bulbous heat shield. The heat shield is required for protecting the satellite when the rocket or the satellite launch vehicle goes through the atmosphere at a high speed and till the atmosphere thinks out beyond what is called 80 kilometers is what NASA says. The International Space Union calls it 100 kilometers. Beyond that, at least in that level, the heat generated has to be prevented from entering the satellite chamber. So we have what is called the heat shield. It's a specially designed chamber where, and it has to be very lightweight as well. So closed loop guidance is what we call is the attitude control system. And digital autopilot is what you see the countdown and the automatic control system by which the rocket systems which are now, which the live transmissions come, you see that they say theoretical path and the actual acquired path. So the autopilot is what controls the rocket and takes it to the desired orbit and attitude. So this paved the way for the PSLV and the GSLV. So PSLV is the Polar Satellite Launch Vehicle and GSLV was the Geostationary Satellite Launch Vehicle. I'll come to that next slide. So then comes the phase of 90s where major space infrastructure was created under two broad classes. One for communication, broadcasting, meteorology, and through the Indian National Satellite System. I'll expand on each one of these. And the other was the Indian Remote Sensing Satellite System. And simultaneously, the launch vehicles, Polar Satellite Launch Vehicle and development of Geosynchronous Satellite Launch Vehicle were significant achievements. So the 80s and the 90s saw the maturity of the technology, and these were what we call the founding years effectively for making ISRO what it is today. So the Indian National Satellite System initially 1 and 2 were actually taken from through a bought out system from US companies, and these were launched by the Ariane system abroad. And at this time, it was found that as we ourselves made the Indian National Satellite System for our SATCOM as well as remote sensing, that is meteorology, it was found that the cost of making the satellite is in a few hundred crores, but the cost of launching the satellite is several hundred crores. So as a result, there came the push to make a launch vehicle of our own and also not be what is called strong armed by other countries that okay, you cannot launch your satellite on your own, so what space technology you are going to do yourself. So we have to have end-to-end capability. Development of the launch vehicle gave us the end-to-end capabilities. The Indian remote sensing satellite system was once upon a time in the 90s and in 2000 in such an excellent stage that it was considered the number one civilian remote sensing program, including in the after 2010 onwards. There were a large constellation of our remote sensing programs, and that tradition and legacy is still going on as the lifetime replacement of each of those satellites is going on. So geosynchronous satellite launch vehicle and polar satellite launch vehicle, these are the two basic different type of launch vehicles. And the polar satellite launch vehicle means the one which takes it to the low Earth orbit up to about 700, 800 kilometers and releases the satellite up to about 6 to 7 kilometers per second at the desired point. And the tonnage capacity of the PSLV with all augmentation was approximately 1100 to 1200 kilograms. But with extension and with additional strap-on boosters, it was used including for the first METSAT or Kalpana 1 satellite for geostationary later on, and then finally for Chandrayaan 1 as well, and for Mangalyaan as well. Simultaneously, we created the Geosynchronous Satellite Launch Vehicle, GSLV. So today I am not touching upon the GSLV much and concentrating more on the other aspects of it. We will take up that at a later stage and some of the other projects, because the number of projects ISRO has are so many that I will have to spend a few hours with Sabyasachi ji, I hope provides me in future. Okay. And see, basic difference between PSLV and GSLV is that the GSLV rocket makes use of the liquid hydrogen, liquid oxygen or the cryogenic stage at the last stage. The solid booster part, concept wise, they are much larger. Concept wise, they're similar. But in terms of capacity of launch, the GSLV is a much larger platform for launching satellites. And this development was carried out in the basic 90s and the 2000 years. Sabyasachi, next slide. Okay. So some missions which were milestones in the ISRO's path or long journey. IRS-1A, Indian Remote Sensing Satellite 1A, was my first project which I started working on was the camera sensors for them. So it was the first series of indigenous state-of-art remote sensing satellite, and launched on 17th March 1988. Soviet Cosmodrome Baikonur, because those days we didn't have a launcher, so they used a Soyuz rocket actually. And there were two sensors, LIS, linear imaging self-scanning. LIS stands for linear imaging self-scanning. So the linear imaging is done by the detector which is placed in the cross direction of the path of the satellite, and self-scanning is as the satellite moves in its orbit, the scanning goes on as a strict path. And these two had a resolution of 72 meters and 36 meters. 72 meters is the resolution as seen from the satellite top down to the Earth's surface where it is looking at, and 36 meters, and a swath of 140 kilometers during each pass over the country. It could take photographs across the world, but it did not have any solid state recorder, so it could take photographs and immediately download. It was part operational and part experimental mission to develop the Indian expertise in satellite imagery. However, the products from these were found to be very useful, and they created the entire environment of remote sensing applications in our country and set us in a different direction altogether. Another milestone I will say is METSAT or Kalpana 1. Why I have specifically mentioned this is that today's discussion is more on the Chandrayaan part. The actual precursor for the launch system for Chandrayaan 1 using the PSLV rocket in those days was actually the METSAT. This was the first time that we actually used the PSLV rocket for creating a geostationary launch. It was meant for polar launch, but we actually augmented it, and some of the visionaries of the rocket engineering thought that it could be done. So that is the reason why I specifically mentioned METSAT. It was renamed as Kalpana 1 after Dr. Kalpana Chawla, who expired as an Indian citizen, ex-Indian, Indian-born American astronaut. Next slide. Okay, so these are the specifications of METSAT. And this being the first what we call indigenous geostationary satellite and launched as well from India. So it was an actual great milestone. So the spacecraft mass and dry weight. Now, here I will come one by one to something. The basic mission is meteorological. The mass of the satellite at liftoff is quite high because the spacecraft launch vehicle is going to leave it in an elliptical orbit around the Earth with a certain inclination and orbital velocity. And then what is called the apogee boost motor, or the motor rocket, which is inside the satellite itself with its own fuel, will burn, and as a result it will push it to the final orbit, which is the actually geostationary orbit. There were two sensors in this, very high resolution radiometer or called VHRR, and the data relay transponder, also called the automatic weather station system. Launch was on September, that's okay. And the basic launch vehicles, PSLV C4, so at 74 degrees east longitude, we had placed it. But this was the precursor for ISRO learning the basic technology of utilizing the boost system to upload slowly and steadily a satellite from Earth orbit to non-Earth orbit, or crossing that 11.2 kilometers threshold. So this was the first one where that attempt was made, and hence I tried to put this in more detail. Next slide, Sabyasachi. Okay, now I am straight away going to the lunar mission of Chandrayaan 1. Chandrayaan 1 was a landmark mission because it is the first time we tried to escape the 11.2 kilometers velocity of the Earth. Going out of the Earth itself is a great achievement for any country. See, because you need a vehicle which can exceed that velocity. Even though we may have used the boost mechanism of the Earth, and slowly it may have taken more time, as it did even in the case of our Chandrayaan 3. So the weight of this was, liftoff mass is 1380 kgs, and the mass will be always larger because the fuel is part of the satellite itself. And 3x is stabilized using reaction wheel and attitude control thrusters. I'll take some more time on this because the same concept is used in all of our satellites today. So 3x is stabilized using reaction wheel and attitude control thrusters, sun sensors, star sensors, fiber optic gyros, and accelerometers for attitude determination. These are some technological terms for stabilization. 3x stabilization means that we have in the satellite what is called a earth view plate. The earth view plate, which is always looking at the Earth. Now, to maintain any remote sensing satellite, satellite communication satellite, if we don't have a 3-axis stabilization, then the earth view plate is not stable. The stability of the earth view plate, the one surface or the cuboid has to face the earth always, and hence we create the three-axis stabilization. The Let me give a simple control system example that the human being is three-axis stabilized. Okay, we are not falling down when we are jumping, even though we are facing so many forces. We are able to climb upstairs, climb downstairs. All that happens because of this control system, and that is what differentiates the human being. Our two hands and fingers, which are very adaptable, and this is what differentiates human beings from all other mammals as well. That we can stand on 2 feet and we are three-axis stabilized. To put it in simple way, to create a three-axis stabilization in orbit, which is basically any satellite will become a tumbling system actually. So we have to forcibly make it stabilized because we are now already in microgravity. The earth is not stabilizing us anymore or keeping us straight. So for this we read the details. I don't know whether I should go to that detail. How much time I have spent? 25 minutes. Okay. So this is the reaction wheels actually, and the momentum wheels which are there. Generally in ISRO satellites we make use of 4 wheels, one wheel for each of the direction. In satellite the direction is called roll, pitch and yaw. So we have actually 3 wheels on the axes, and a fourth wheel which is a redundant wheel to all the three. And these are highly spinning wheels, similarly to the flywheel actually. And the edges are very much thick and the central part. So the momentum of these wheels rotating at a specific speed will be very high. So this provides the stability to it. And the attitude control thrusters are, if the thrusters are actually meant that if there is a force major condition, then the initial stage orbit acquisition as well as the stabilization of the orbit, what is called the station keeping. For station keeping, we have to fire the thrusters occasionally. And these thrusters are based upon the stored high pressure gases and oxidizers. Then sun sensor, star sensor, fiber optic gyros and accelerometers for attitude determination. How do you know that the earth view plate is actually facing the earth and not facing the null? Null means the deep space side. So for that, the sun sensor is mounted at a particular position. The star sensors are pointed to a particular constellation which is giving sufficient contrast. These are specific electro-optical sensors. And the gyroscope, today there are no more fiber optic gyroscopes. We make use of better what is called ring laser gyroscopes and accelerometers. So these will provide the attitude information which is fed into the complete what is called attitude and orbit control system. This is a complete subsystem and is considered a nation which can develop an AOCS system for a satellite, can do that same thing for also military systems as well. So this is a great achievement which we could do it. And as a result, now this is now considered that okay, we can anyway do it. So it's considered the normal now. The scientific payloads from India for Chandrayaan 1 were, the major ones were terrain mapping camera, hyperspectral camera. These were developed at the group where I was working actually, the TMC. And here the TMC and hyperspectral are actually quite important because they played a serious role in. And another was the moon impact probe. So I was requested to give some inside information or something to that. So I will give that actually. Laser ranging instrument was actually created by some other center of ISRO. High energy X-ray spectrometer was a physics payload. And here the payloads from abroad includes one payload which is of importance, and that is the M3, Moon Mineralogy Mapper. This was from NASA. Now, the first important milestone of Chandrayaan 1 was that it was the first lunar mission which found what is called trapped moisture or trapped H2O in the signature of the trapped H2O in lunar or moon regolith. Now, on Earth, what we call sand, the same we call it regolith on moon. So this is actually the multi-mineral fine particulate cover on moon. It's also having a lot of static electricity is what has been known now. And utilizing the hyperspectral imager as well as the confirmation from the moon mineralogy mapper, it is also a similar like hyperspectral. The actual signature of H2O was found from the reflected light. So this is one significant thing which came. Second comes the terrain mapping camera. Now this terrain mapping camera was unique and it was being used in all the Chandrayaan 1 and Chandrayaan 2. And this played a very significant role for both, I will say, the attempted landing on Chandrayaan 2 and the actual successful landing in Chandrayaan 3. So this terrain mapping camera, I have some more slides on this, I'll tell later on while I'm actually terrain mapping camera kya karta tha, that I will describe it. Okay. Now, one more important thing was the moon impact probe. Now, this moon impact probe was a last minute addition from Dr. Abdul Kalam sir. He gave the idea that if we are actually going to moon, let us put some sort of stamp on moon. Let us land something on moon, even though we don't know something. So an impactor was created along with a camera mounted on the top side of it. So that camera was actually from our group, and we were the first people who actually got that spin stabilized photograph of the moon. These are available on the web. People can see it actually. So it was his very excellent idea which he gave, and at the last moment this moon impactor probe was put. So, and the Chandrayaan 1 actual spacecraft, it released that moon impactor probe at a particular point, and it gave the videos, and it is the first object from India which actually went and landed on moon. So this important. This does not come out in normal parlance, but the moon impactor probe was an idea which Kalam sir himself had given. So it was a great achievement. And the orbit was put, generally we put it in 100 kilometer by 100 kilometer. It was launched on 22nd October, and these are all known, well known. Can we go to next slide? Okay. So again, in lunar mission 2 Chandrayana, I have only put the orbiter payloads because actually the Vikram lander and the Pragyan of Chandrayaan 2 did not become successful because we could not land successfully. Let us not attribute it as a, see, because landing on moon is not at all an easy matter. Let me put it like this. It's a what we call what we today pass off as artificial intelligence. It is more higher level of artificial intelligence than anything which we have on Earth actually. Let me tell you that it is too complex, and the type of landing which is required, the actual materials which are required to land on the moon, how to take care of the electrostatic surface of moon, where even sometimes communication may happen, may not happen, and sometimes you don't have visibility. The actual control system which is transmitting, or the data system which is transmitting, is again another orbiter platform. So the orbiting part has to receive the data from the lander all the time, and it has to be autonomous, fully autonomous in the landing. Anyway, the orbiter carried again the terrain mapping camera, and the another very important payload which was there is the orbiter high resolution camera, or OHRC. We also had an imaging infrared spectrometer, as well as these are all the science payload, dual frequency synthetic aperture radar to find out the distance, and they try to map the moon surface using a radar, and dual frequency science experiment. These were some of the other experiments. However, there is one interesting thing about the high resolution camera which I will bring out here. Incidentally, the high resolution camera, which again was developed in the same group where I worked actually. So this has a resolution on the moon surface of 25 centimeters plus, better than that. So we have a camera on moon which can see at 25 centimeters, but the best camera with which we can see the Earth is about 35-40 centimeters. So this is a unique capability which we have, put it in a different way. And the terrain mapping camera, I have another slide on that, because it provided what is called the two were put, and what it is and why it was put, that also has a very important role in actual landing missions. So we'll come to that. And incidentally, India is the one country in the world which has created what we call a map of the moon in a way which very other few countries in the world have. Maybe only possibly NASA has such a similar system, but they have been taking to moon from more than 4 decades. So, but we have been doing this in the last about 15 years as well. Next slide, please. Okay, so this is more about the Chandrayaan 2 terrain mapping camera. So why this terrain mapping camera is important, I'm trying to focus on it, and as one of the sample instruments actually, which was put. So the terrain mapping camera actually provides what is called a stereoscopic view, and it creates what is called the digital. From that information, we can create a digital elevation model of moon. So we can find out which part of moon is a crevice, which part is a crater, which part is at what height, based upon the 3 images. So this is a 5-meter spatial resolution and stereo triplets, 4 nadir and aft. So 4 nadir and aft, I will put it like this to you, that there is one, this actually a sort of a triangular shaped camera which we had developed. One is facing the down section, another is facing the triangle forward section, and another is facing the aft section. So it's normally when we do stereoscope on Earth, we see literally, and we combine to 60 degrees common overlap view, and then we try to create a stereoscope. Here we did it in the travel direction of the Chandrayaan. So as it is traveling, the first camera is viewing it, the second camera is viewing with an overlap, and the third camera is again viewing with an additional overlap. And from these three cameras, the data we created what is called using they were panchromatic cameras, but the colors were assigned to those in the common areas. So this is how the data products were created. If you can read it, actually the 4 camera nadir and aft view camera, and then from that we create a digital elevation model from which the stereoscope we are able to create the height from this. And this again, I have few more photos of this. Sabyasachi ji, you can go forward. Yeah. So you see that these are unique images which India can create, and this is still working. Let me tell you that even Chandrayaan 2, I don't know whether it is now decommissioned or not, but it is still working. And these are the exact what we call 5-meter views, and in some cases the resolution has been improved further because of the very high triplet data available actually. And using this actually the landing position of Chandrayaan 2 and Chandrayaan 3 were determined. This has played a serious role. This TMC or the thematic mapping camera which was created for this. So that's why this slide I have put actually. So it's a typical electro-optical instrument which was highly successful and has an international recognition. Now Chandrayaan 3, actually I request the audience to go over to the isro.gov Chandrayaan 3 details.html, because there is too much long information about Chandrayaan 3. So I think Sabyasachi ji, we have enough time to cover something on Chandrayaan 3 today.
Yeah, we have enough time.
Yes, okay. So I am going over to the link actually. I request all to go over to the link on Chandrayaan 3, because in terms of Chandrayaan 3 was actually launched by the GSLV rocket, and the overall weight is nearly 4,000 kilograms. And all our satellites which we launched to geostationary orbit, we make use of the apogee boost motor, and that is we use what is called the push, as the Earth sends us to a orbit in such a way, elliptical orbit, that once we come close to the Earth and then we again go very far from the Earth, and at some point we make use of the boost motor and change the trajectory, and slowly the Earth itself increases the velocity. The first use of such boost, very famous, was the Voyager, which actually made use of the Jupiter boost to go beyond Jupiter. Till Jupiter, it was traveling at just about 11 plus 12 kilometers per second. But after Jupiter's boost, it started traveling at almost 27 plus kilometers per second, 26 point something kilometers per second. And as a result, it was able to then pass beyond Jupiter. So this system is described in certain NASA, what we call it's called the ping pong ball system, that as you sort of push towards the planetary gravitational force, the gravitational force gives you then equal push, and you actually start rotating at a faster and faster speed. So as a result, this gravitational boost assist was used in all our satellites which we try to go beyond. So Chandrayaan 3 has 3 parts. That is basically the orbiter part, the lander part, and finally what we call our small Pragyan, choti si gaadi. Okay, it's very small, but possibly the costliest car India has made. But it can work on moon. That is the big deal. In moon pe there is no driving license required. No issues. Okay, to put it nicely. So there were various payloads also in this, and the launch videos, everything are there. So few insights I will give over here. One question is always asked to me by young people, that why only 14 days? To understand that moon is sort of nearly because of the Earth, close to Earth. So its rotation period and its orbital period, revolution and orbital period, is nearly same. So as a result, no, please keep the same slide. Okay. Yeah, I think Sabyasachi ji, everybody can is seeing about Chandrayaan 3.
Yeah, right. Everyone is seeing the Chandrayaan 3. Yeah, right.
Okay, fine. So the basic concept in Chandrayaan 3 you have to understand is that once you reach the orbit is put in a specific what we call required orbit, whether it is Chandrayaan 2 or Chandrayaan 3, then we have to release the lander and the lander has to come in a trajectory by which the pre-designated site, in the case of Chandrayaan 3, it was near the south pole of moon. So it has to go towards the pre-designated site. So all these automatic calculations have been done in advance. The point at which it has to be released, its trajectory, its inclination, its angle of attack, and from that it has to go down on its own. And the most important thing is that moon has no atmosphere, so there is no braking force. You have to brake on your own. So before this, I will say a few more things actually. In space technology, if we want to go to moon or we want to go to Mars, we have to understand one thing. There is no braking system. So the amount of energy which we have spent, let us say 11.2 kilometers per second, cross the earth and go towards moon, we to get the entire spacecraft captured by moon. It's called the moon capture maneuver. And this is a very crucial maneuver. This also the first time several people actually failed. Let me tell you that in 60s, those who went to moon, 70s, some of the Russian missions, they went past moon and they simply went away. So the rocket has to reduce its velocity in such a way that it comes in the what is called the capture gravitational pull zone of the moon. Unless otherwise it is not captured by the moon, then it will simply fly away from the moon. And the bigger problem is that once you go away from the moon, you cannot come back. You don't have that much energy left in you. The same thing was very crucial even in Mangalyaan, which I will treat at some other place. So this is one crucial maneuver, and that is called moon capture. So moon capture, once it is done, then we have to stabilize the orbit exactly like any satellite which we do on Earth. So it has to stabilize the orbit. It has to, after stabilizing the orbit, it has to open its all systems. Spacecraft has to open the systems. It has to get its solar power done, everything done. And there is another thing which has been always done, that while we leave the moon, we try to also take, in the case of Chandrayaan 3, I think it was not done. In Mangalyaan, actually, the cameras were switched on the way, and it took the images of Earth itself while going towards the Mars mission, actually. So here again, as it is there on everyone's slide, so the purpose is very well known. And after achieving the actual orbit, which is actually the moon orbit around 100 kilometers, the release is done. So 14 days क्यों चलता है, that I will try to answer. So once the moon day is there, we can protect the satellite utilizing our large solar panel and keep it in a shade, and we can have the power itself to cool down our electronic boxes as well as the mechanical boxes. But the point is that once it goes to the night part of the moon, you see the moon itself where we land, it is going to have moon. We can't see that part from here because it is tidally nearly locked. So 14 days. But once it goes to the darks, or what the non-illuminated or the night part of the moon having no atmosphere, the temperature dips to almost around below minus 200 degrees centigrade. And the moon, when it is actually in the daytime, or when it is in the lighted time, so there again is a huge challenge. If the temperature rises to about 300 degrees centigrade, so we have to protect the entire box during the actual daytime of the moon. And during the night time of the moon, there is no way. The entire electronics, everything, because it is so cold, the batteries itself will freeze. Even some of the electronics or the PCBs which we have, they will not work. The only way to do it, to keep it working, I understand that now the CNSA, or the Chinese Space Agency, has put the necessary, what we call some sort of nuclear heating system in it. And as a result, they have been able to go to what is called the dark side, or the non-illuminated side of moon, and survive more than 14 days. So as of today, we did not have such a plan. So this was the first mission. So we had a 14 Earth days maximum after landing, and accordingly the release of the lander is also done in such a way that we land at a point where we can actually do full 14 days of sunlight illuminated time, so that we can make use of the maximum and carry out the maximum demonstration. So the landing site was 4 kilometers, 2.4 kilometers. I am reading from the website actually. And the actual location was, these are the moon coordinates. So this is the moon coordinate near the south pole of the moon. And the landing was carried out successfully. And the most important thing is that the large number of cameras which were there, lander hazard detection, lander distance measurement, all these cameras which are now no more now considered even payloads now, actually. They are not even considered payloads. They are now considered part of the spacecraft itself. So we were part of the team which was actually developing all those cameras. So some of the cameras were high resolution, some of the cameras were very low resolution. There were some of the cameras on the rover, for example, they are button cameras like your mobile, but still they are developed in such a way that they can give us reasonably good images. And uh, so the entire videos, everything we will be showing them as well. So that is there. And these are actually Rambha, then surface physical experiment CHAST, then finding out what is there on the surface, then instrument for lunar seismic activity. It appears that our seismic activity has actually successfully detected some seismic activity as part of the 14 days operational time. Then reflectometer array, LRA, I'll be covering less of this. Alpha particle X-ray spectrometer, this is again a science instrument which tries to find out what type of particles are hitting the moon during the time it is on. And breakdown spectrometry, we try to fire a laser beam and then try to find out that with see that what sort of moon surface data we can collect from these. Okay. And there is a spectroplanetary polarimetric habitable planet Earth. So this was looking back, the shape payload was looking back at the Earth and try to find the type of environmental parameters looking from there. Okay. Spectropolarimetry of habitable planet Earth. Okay. The details I will cover in maybe in a next session actually. So more importantly, the entire landing process was carried out using completely autonomous mode, and the utilizing the feedback which it was receiving from the images. There was a real-time image correction mode, and based on those images, the landing control computers, they were able to create the legs to go down exactly at the point where we wanted to land. And as a result of the entire enterprise, we were able to slowly land the entire process, and then we had to create the firing done in a particular known and pre-planned systematic manner. So the firing has to be done in such a way that the velocity slowly comes down from the release velocity, which is almost about, and the additional velocity which comes because of moon's gravity. So this velocity has to be reduced, and the final velocities were achieved at the order of 3 to 4 meters per second. And then the landing was done successfully. After this, then the rest is obviously what is called, now it is history, that we could get the Pragyan rover out of the slide, and through the slide opened, and then the Pragyan rover went around, and we have the videos also of. So these are the details of the actual technology, and maybe someday I will go for the entire technology discussion and carry out actually. So today we will just pass it over Sabyasachi ji, right? Okay.
Yeah. So
And
so
the
so right now, can we show the some of the videos of Chandrayaan
yeah,
3?
yeah, I think we can show the videos actually. And okay, no, just a moment. I'll just show the photograph. If people have the photographs, these four lander legs, and then the actual what we call the payload, so the entire thruster and everything. You have to understand that this is a several level type of spacecraft. The orbiter itself is a huge spacecraft. Inside it is another spacecraft which is actually going to land on moon. So it has its own propulsion system. It has an additional attitude orbit control system, and it is able to land back on moon. And from there, we have, from that box, we are taking the Pragyan vessel out. The lander itself, after landing, also has its own spacecraft, plus it's like a satellite with its own payloads. So this is quite a complex system, and in detail, maybe someday I'll cover it in. Okay. And it includes everything. It is completely self-contained system which takes care of the solar power system. It has its own batteries. It has its own antennas. You have to understand that the lander, once it lands, it cannot communicate. It communicates through the orbiter actually. And one important point I will bring out here is that the communication in any extraterrestrial Earth mission is done using a format which we call as the CCSDS format, and now it is also called the ISDN format. So it is International Space Data Network, and this is India alone and its ground stations cannot see the moon at all time. So the commands are uplinked through several ground stations of all the nations put together. There is a space collaboration also, and similarly during all our uh, satellite launches also we have collaboration. And these ground stations across the world, whether it is somewhere in Norway, Canada, somewhere in Bayak, somewhere we have in Mauritius our own now, and even in Antarctic we have our own now. and several other places, NASA, Deep Space Network, all we collaborate together. They receive the data, we send the data or commands to them, and they upload it for us, because the moon will not be visible always from India, because the moon will be visible. Night is different and Earth is different, so Earth itself rotates. So this is the international collaboration, and because of collaboration, there is a standardized format across the world for all the data transmission and the data commanding. So this is covered under what we call as the ISDN format actually. So I think we can show the videos now.
Yeah.
Okay, this was actually a video of why we were actually landing. So I have taken it from the ISRO website. So as we were landing, the image was actually taken, and then we can go for the next one. Okay, it's a very short video. The photo of the Pragyan rover. Yeah. So this is actually, we are viewing the moon from the orbiter actually. This is the pre phase where our lander is actually going to land. So it's actually the video taken from there. Okay. And this is another video.
Yeah. So
Okay.
should I
So
go to the
yeah, you can switch back to the So the now the overall capabilities of what we have today, we have Earth observation satellites. I have not written down much about the communication satellites, but they are the INSAT series of satellites which we have, and the GeoSat or INSAT series. So we have capabilities in the LEO, that is low Earth orbit, and the GEO, that is geostationary Earth orbit. We have capabilities in optical, thermal infrared, and active microwave, as well as in cartography. So cartography is considered one level above in terms of resolution from remote sensing, because the remote sensing data is actually at a slightly lower resolution, but at a much wider type of bandwidths and something like that. So some examples I have given here is a advanced wide field imaging system. This was used in ResourceSat 2, and it is very useful for, because there is a photograph attached with that also. So it's a 56-meter resolution suitable for state level analysis. And it has bands operating in 3 VNIR. VNR means visible and NIR bands, and one in SWIR, that is shortwave infrared band. So, and similar to the LIS 3 sensor which was used earlier actually. So swath, a combined swath of 740 kilometers achieved by 2 camera modules, enabling a quick revisit time of 5 days. So this actually can give us what we call a full imaging of the country, which we have in 740 kilometers, means in 3 swaths we can almost cover east-west easily, and or nearly 3.5 swaths. And so every 5 days we can visit the same area again and again. As a result, we are able to achieve from this AWS what is the green cover of India, where it is going to rain, where it is not raining, and the features of the country, how it is changing, the river widths also, everything. These are the remote sensing applications which are carried out. So it was built on the experience of the earlier WIPS payload, and this was the advanced actually. And you have to understand there is a very large what you call, this is an AWIPS actually. This is converted back to green color, because normally the color which is seen from satellites is false color, and the FCC actually. So this is converted back to real color. So the green is shown as green, and you can see the Ganges River, Brahmaputra River very clearly over here. So, and the coastlines, and even this data is so good. Let me get to that photo. Yeah, I'll explain this photo over here. See the resolution of the radiometric, no, not this one, sir. Previous one. I'll explain the photo a bit. Yeah. See the Sundarban area. I have chosen this photo because it is the eastern part. So, and this is the river delta which is coming out very clearly. Okay, I can't point a mouse over here. That's not an issue. I'm pointing on my camera slowly. The Ganges river and every tributary of Ganges can be also seen very clearly. Then the cloud cover of Himalayas, and this is actually satellite photo which is taken from the entire part. Similarly, that the greenery part where there is no greenery, that also comes out very clearly. And most importantly, I request the all to focus on the blue part. See the shades of blue after Sundarban, south of Sundarban. Okay, so the south of Sundarban is as the river is going down, you can see the shades of blue. So this shows that the amount of what we call the change of color in the blue shows the amount of silt which is actually going from the land to the sea, and the different shades of blue also show the depth of the sea and the type of biomass in this area of sea. So this is the type of what we call remote sensing applications which come out from satellite imagery. We can go to the next slide. These are two views which are actually this is the remote sensing applications at the LEO level. The type of data used in India, like I showed the previous AVIPS or the ResourceSat VNIR and the Oceansat data, there is still enough competition from other satellite companies like Space Imaging, from Sentinel, from Maxar. But in the field of geostationary meteorological data, there is no other option for India. So they are the only satellites which are giving now more than 48 images per day. And this is available from the IMD website. On every 15 minutes, they are now giving every image sometimes. And they are extremely useful. So if there has been one satellite of India which has saved the maximum number of lives in India from cyclones, then it is the INSAT series. So in some of my social media posts, I have even written. And second, this is one of the great achievements, because to view the earth and your own country from space back is something which only I think 4 countries in the world have. So this geostationary orbit, actually, I have put actually 3 images: the INSAT 3DR, which was the first day image, and this is actually a VHRR image, the first one on the left. These are images are taken from this is the actual instrument image. So the grid fit is not done. The latitude longitude fit has been not done. So this is the actual instrument image. The white areas are the clouds, and the from the shape you can actually make out the Saudi Arabia and the African coastline on the east side from the image. Okay. Now here from there is some interesting insight I will tell you, that in satellite technology or rocket technology, we don't make use of any east-west direction or north-south direction. For us, the actual directions are roll direction, pitch direction, and yaw direction. So there is no other direction. So, and the satellite axis is actually from null to nadir. So our language is different. So if I start using jargon here, then you are not going to call me again. So I will avoiding it. So what is east from the satellite is actually west on Earth. So in this satellite, the first image actually, the satellite actually scans from east to west, but the image appears from west to right. So these are actually available live on the systems which we have at Delhi, and these are most useful for us for predicting not only the weather but also finding out where it is going to rain and everything. And there was a sea change in meteorology of our country after these satellites were launched. And actually, for a country like India, which has so much varied weather and severe environmental and I will say rainfall issues, sometimes rain is there, sometimes excess rain is there, this satellite has proved to be, I will say, not only weight of, possibly its weight in diamonds more than gold itself. So it's something which is most essential. And these are also part of what is called the multi-mission satellite. The INSAT also has some satellite communication antennas also attached with it, and along with that it has meteorology stations. So it makes it very challenging, because to operate, I have not put an infrared image over here. So those of you who are interested in infrared, you can see it. To keep an infrared detector, you have to actually cool the detector back down to minus 190 degrees temperature. Only then you can make out what the cloud top temperatures, which are about minus 60, minus 70, minus 90 degrees. To get such images, you have to actually cool the detectors to very low temperatures. And we have actually to cool the detector. I think I should explain some basic technology here. that satellites cannot cool. There is no fan, there is no air out there in the satellite space. So the only way to cool is radiative cooling. The radiative cooling is that we have pipes which carry a few type of liquids from the hot areas, and this radiator actually looks at the null. That in null means the direction away from the earth, deep space. And these radiators will throw the heat out, and they will be operating at nearly very low temperature. They will achieve very low temperature, and this cooling, or to say it's a passive or sometimes the passive cooling system. So hot and cold cycle will go on happening, and as a result, the satellite will be cooled. In this case, the infrared, true infrared, what we call images, which we have, they are in several bands, TIR1, TIR2. You can go to the website and see them as well. So these are actually operated at such a low temperature. So the detector itself is put on a plate which is actually looking away. So there is a huge sort of a it's called it's a the a pentagon shaped actually is there. It's more like a what you call a rocket's nozzle, and it's a square shaped platform, and on that we call it a patch. So that patch is again reheated back, because that patch will again hit minus 240 degrees centigrade, because it is looking at null and very, very low, not exactly 240, but it will actually hit nearly around minus 260 to 70 degrees. So we heat it back and bring the temperature of the desired detector to that level. But however, the INSAT satellite is actually in full service, and the most important thing is that being geostationary, it is able to give images every half an hour for our nation's use. Next one.
This is the last slide, sir.
This is the last one. I think we can take some questions now.
Yeah. So we have a few questions. Some of them are trivial. Some of them are a bit in detail. So, yeah. So starting with one trivial questions. So Rita wants to know what is microgravity. Yeah.
Okay. So microgravity is something like this, that the moment you go a certain distance away from Earth, so we don't realize what is gravity just because we are on the surface of the Earth. So it is so good for us. So many things become very bad. The moment you start leaving the Earth and you go to a certain distance away from the Earth in terms of the radial distance from the center of the Earth, so the pull of the Earth starts reducing. So these are standard what we call gravitational formulas, that what for the mass of the Earth and its density, what would be the gravity and what is the sphere of influence which we have. And this is again based upon at distances. So microgravity means that the you are not at all actually what we call in a position to get a reaction force from any surface. You become a free body. You become completely free body. So once you become a free body, I'll tell you one very fascinating insight. Actually, I'll tell you. Let me give an example in terms of, let us say, Mahatma Gandhi's theory of non-violence. Okay, so you will understand what is microgravity in a different way. Let us take what he said is, if somebody slaps you, you are supposed to offer a second chin to slap again. So, but what will happen if, let us say, inside a space station which is in microgravity, there is a big quarrel between the two fellows, and one fellow slaps him. So the problem is that there is no violence, non-violence out there. So that is microgravity. I will explain simple language to you. The person who slaps will go in the backward direction, reverse direction, full speed. He will go and hit some manifold. The person who gets slapped, he will also go and hit some manifold. So this is fascinating example of microgravity, that the definition of non-violence on space is different. The person who got hit, he is equally violent because he caused hurt to the fellow who started hitting you. So this is a very nice way I can try to explain microgravity. So the effect of gravity is not there beyond some point. And as a result, once we cross that threshold, the Earth's gravity will go on reducing. And at some point, we will feel that now we are become a free body. This is also emulated sometimes in, there is a famous European Space Agency plane where the training is given to people, and they can also go and they actually create a dive. So, and people start flying inside the plane. So then once you, effectively, I will say microgravity is such that where the effective 9.81 meter second square force is countered effectively at a zero level, and you are not going to face that force at all.
Yes. So microgravity is a gravity where the gravity is almost zero.
It is nearly zero.
Yeah, it
So
is
if you
really.
slap someone, you are going to get equally hurt. And Mahatma Gandhi's theory of non-violence doesn't work over there. So I'll put it in a nice way.
Yeah, yeah, yeah. So Orgo wonders whether these videos are real. So he's
These
asking whether
videos are. This
all of.
is a question. These videos are from the original ISRO website. And let me tell you one very important thing, that these videos are real because the light angle of the moon. Okay, so the light angle at which the expected moon landing has to happen, and the light angle, the way the temperatures are should be, and including, if you see the actual landing video, you will see, because this is a question, because doubt. And surprisingly, my department is responsible for actually showing the where we were working the actual cameras of landing, because I fully agree with you. Nobody will believe that you reach the moon if you can't show a photo of moon. So that is one most important thing. And secondly, the videos which have been put, they were actually taken in the form of, they are not MPEG videos. Let me tell you that they were actually what we call a series of photographs, MJPEG, and these MJPEG have been combined to create the photographs. So it's about the reality part of it. I will tell you that their actual individual photos also exist, that this is actually happening in a sequence. And most importantly, that it is the moon surface is confirmed from the locations of the moon. So you can't create the what you call a artificial intelligence generated like that. I don't know with what context he is asking the question, but that's what I believe. Maybe I could try to answer him.
Yeah,
Okay.
probably he's not. He's just wondering. The picture is so nice, so that he's just wondering whether these are the real or. Okay, so Utpal is asking whether these videos are taken from orbiter or from the lander.
Uh, I think there is the link which has been put. You will see that each one of them has been taken. The from the lander, when it was landing, what is called the lander hazard detection camera. There are videos from that as well. So I think you can go to the website and see all the videos are available. And the
Yeah,
run length videos from OHRC as well as TMC, they are also available. So
yeah,
they are all on the ISRO website, and they are all genuine videos which are actually put by ISRO from the actual cameras. And let me tell you, so far as the previous question is concerned, there is a International Space Data Center in India, and the International Space Data Center actually stores and archives all the data. So if you are a recognized scientist, you can actually request for the data, including some of those videos actually, and you can actually get the information.
yeah. So there's a question from Sanchayan. He's asking whether in the field of agriculture and disaster management and climate monitoring, how ISRO is working.
Okay. So see, the space segment part of it is actually what we call uh, the how it is contributing, that the from SAC contributes to satellite data from SAC. See, first of all, let me tell you like this, that satellite data is not exactly from SAC. So I'll expand on his question and put it in a very nice way. Just a moment, let me get a paper actually. In space technology, they see the entire thing of space mission linkages is something like this, that there is a for linkage. The for linkage is that for the payload, that is the camera, what Sanchayan has actually asked the question, we have the satellite, and for the satellite we have the rocket, and then we have what is called the unless loop. So unless there is a rocket which takes it to the orbit, and unless the satellite works, then only the payload will start working. Okay, the application. And there is a if loop also. If the rocket works, then the satellite may work, and then the payload will work. But the reverse loop is that the camera or the payload, if it does not work, then every rocket, every satellite fellow's effort is gone. So the payload is at the top. So I'll now answer his question, that SAC is not exactly generating. SAC actually makes the payloads for Indian satellites. So both the remote sensing as well as the communication antennas, and including now the microwave systems as well, microwave remote sensing completes packages, we develop it. So we call it actually one of the systems or the payloads which are mounted on the Indian satellites. So there is a huge field of remote sensing applications, including both government sector as well as private sector. There are very large, the largest field for space applications or satellite applications in India is actually the field of remote sensing applications. And these remote sensing applications is majorly used by agriculture, then land use mapping, urban planning, as well as what we call weather monitoring. And as I give the example of weather monitoring and weather forecasting, and in also now in transportation sector. The third is in what we call the other sector is what we call the applications for the special users who use it for the identification of objects, and we also use it for getting the reflected data from the mineral mapping, that is the hyperspectral data. And most importantly, the agriculture use is very, very extensive, including the, I'll tell you, even the insurance of the agricultural crop loss is now measured using satellite data. So they will find out which part of the crop has gone bad, which crop previously, which part of the crop was actually standing in terms of the green signature of it, the satellites. So, and for that, I will expand this question and tell him that, see, every satellite, once it is launched, we have a huge cycle called CalVal. It is called calibration and validation. So the CalVal part of the system is done during the initial phase. So initial phase, what we will do is we will take a radiometer and we will take a signature and find with the radiometer's information how it is matching with which band and which the intensity of which light, which band it is giving that much light. And that correlation will create what is called the CalVal, calibration and validation entire table. The table will be generated, which will actually convert the satellite's raw data to the luminance values for the reflected object on Earth. So you have to understand that optical remote sensing is passive. The light from the top of atmosphere, that is the sunlight reflected albedo, that is measured. And remote sensing is not just taking photographs. It is actually measurement of light. It is a science. It's different from taking photographs. Taking photographs, people will put some small, what we call CubeSat on top and put a mobile phone and then say that I have done remote sensing. That's not remote sensing. Okay, that is just taking photographs. Photography and remote sensing is different because each pixel has a information in terms of its intensity and the band through which it is getting the data. It is correlated with the object on Earth. So for this, we have what we call the image, the information which comes from the satellite. It is considered the raw data. So this raw data, we call it as level 0 data. So level 0 data is not made available to the users. So this undergoes what we call in the Chandrayaan is, what is your age, Chandrayaan?
Sanchan is probably 13 only. He's in school.
13.
But
So he is what, generation X, Y, Z. So Z, okay, Z, end of the alphabet generation. Okay. So by the time you come, right now the language used in satellite technology is, it is called a processing stack. So the stack, what they use is they give out the outputs in terms of several types of products. That is level 3, level 4, and that is called the geodetic fitted data, where you actually map the pixel to a uniform image. Let us say an image is 30 kilometers by 30 kilometers image. So, and the resolution is decided nadir at 5 meters, but the actual product will not be at 5 meters. It will be slightly less. It will maybe 6.5 meters because you have to correct for earth curvature and the off-axis viewing. Off-axis viewing means आप सैटेलाइट से नीचे देख रहे हैं तो वहां 5 मीटर है, तो सैटेलाइट से 20 किलोमीटर दूर देखेंगे तो आपका एंगल चेंज हो जाता है. सो वी कॉल इट अ सेकेंड स्क्वायर थीटा इफेक्ट. सो दैट इफेक्ट विल कॉज ए वाइडर पिक्सल एट द एजेस. सो द मैप is created on a map fitted data. So this data is used by our remote sensing people, and because they have their radiometric information available from it, there are a very large number of algorithms and applied products generated from it. We call it a direct mapping, crop mapping. Then there is something called a NDVI, normalized differential vegetable index, vegetation index. Then similarly, we have what we call the reflected light. So for example, all our solar power stations, they were established using what we call the how much light is reflected from which part of India throughout the year. So based on that, all the solar power companies are establishing that yahan pe light is going to be there is very less cloud cover around the air. So it is called similarly there is what is called the land surface temperature index. So many types of products are there. You can go to a website and find out all these type of products. So this is a extremely useful exercise. And the most important thing is that satellite, once you launch it, you see, this is also a few more things. Few people will say that a rocket works for a few minutes. Satellite works for a few years. Some of our satellites have been working more than 1.5 times their planned life of 5 years. They are going on working, and they stop working only because the fuel runs out. The electronics keeps on working. You cannot go and fill fuel today at 750 kilometers, because it is, the launching a satellite is 10 times cheaper than filling fuel, or maybe 200 times cheaper than filling fuel. So we can launch another satellite. So this is the entire gamut of applications. It is actually helping the country in providing near real-time information, including now the recent monsoons, for example, flood mapping, then environmental degradation, all types of things are done. And this is not only using the ISRO satellites, but also certain foreign satellites people use, and those gaps are filled with, because all remote sensing satellites have a revisit period. So maybe I will come back to you again and explain in a better way.
Yeah. So Virup want to know about a project called Surya. I'm aware of it.
Yeah, what is the status of ISRO's next generation launch vehicle? And I understand it was announced actually just 4 days, so that should be the status as of now. But I can only tell you that most of the technologies for this are already in a matured state. The Mark 4 GSLV or Mark 3, which is already there, it has a capacity, worst case scenario, it can even carry 8,000 kilograms to LEO orbit and 4,000 kilograms to geostationary orbit. It is already launching a satellite of 6,500 kilometers now, kilograms now, and we already have reasonable capacity. So this is a new announcement, and the I will say that in terms of readiness, the confidence level of ISRO in developing such a system is very high, and the improvements which are required in terms of the energy handling is one part of it, and the handling of large amount of energy, as well as the handling of the separation mechanisms, and more importantly the type of payloads which have to be created for this. So maybe more important question here would be that, are we in the process of creating payloads of this size, other than the human space flight payload, which is a crude module that we can carry out? But as of today, the payloads and satellites which we create, they are much smaller, and they are, rather we are constrained by the present system. For example, it is a great effort to create a Cartosat, and we have to mount it in very difficult manner and create a very agile satellite because of that. So if we have better satellites, then obviously the what we call the platform cost gets equated over large number of applications. At present, each launch and each satellite, we have to again go and launching it, so a larger platforms will be also possible. So the readiness in terms of this, how long it will take, I may not be the correct person, because the rocket teams will actually find out the way to do it out. And generally, I will say that ISRO has now a record of success. So I can say that within the next few years, and given the type of momentum now in this matter of creating larger launch vehicles, it will be a success. But I can only answer you that the basic technologies or core technologies required for creating a larger launch vehicle are already in place with ISRO.
Yeah. Sonchan has another question. What exactly made Chandrayaan to crash during the descent?
This was part of the what I was trying to say, that the exact cause of the crash, I don't think there is a public report about it, which I may not be aware of. But overall, we can say that while we were landing, first and foremost, the velocity with which we would have reached the point of surface contact would be more than what is required. And the another thing was that at a certain point, after it had reached a certain height, the communication with the system was actually lost. So one more system could be that the loss of communication. Now, whether it is the physics of the lunar surface, which is a charged surface, charged particle surface, or whether it is a failure of the system itself on the lander, or certain miscalculations, that is still not out as of today. But the fact remains that further you have to understand that when we are actually landing on the moon, we are actually a four-legged system. So you are basically a center of gravity unbalanced system, okay? And you are trying to land in a trajectory. So it's a huge challenge actually. It's a huge challenge. And the fact that we have succeeded, we should clap second time. We have clapped. See, second, Chandrayaan 2 is not a failure, because the OHRC and all other instruments on orbiter are still working. And during Chandrayaan 3, the actual OHRC has taken photographs of even the point where Apollo had landed in 1969. Okay, we have such a high resolution camera. So it is a partially successful project, but the lander could not land. That's also accepted fact.
Yeah. Yeah. Sanchan has another question. So he want to know some behind the screen facet about Chandrayaan or Mangalyaan. So probably you already discussed many of the stories behind the screen. So
Mangalyaan, I think I'll cover separately, which I promised to Sabyasachi
yeah,
sir. So Chandrayaan, few things I will tell you that uh, it may not be a criticism, but I'll say that first the hyperspectral camera did find the what we call a, and the behind the scenes story of Chandrayaan itself is what was the MedSat launch. So that encouraged all our policymakers that okay, even with a PSLV satellite, we could do it. So this has been shown in various ways. There is a movie also on Mangalyaan, which is a dramatized version actually, but nothing like that actually happens. कोई pressure cooker यदि इसरो के भीतर लेके चला है तो उसको वो सिक्योरिटी वाला भगा देगा वहां से. You can't put a pressure cooker in a ISRO campus actually, except for designated areas. So वो सब दिखाया उन्होंने, वो अलग बात है, वो dramatization है. But the fact that the basic behind the scene was that a PSLV, which is considered a very small rocket by international standards, it could actually do it. That is one of the major behind the scene. That is one of the thing. And the precursor to that was the thinking process of our launch teams that, okay, let us first try the MedSat mission. So that was one of the major behind the scene. Second, initially, I would say that there was even a plan to put single cameras, but then the ideas were changed that, okay, we should put something which gives us a stereoscopic view. And this concept of the TMC was created using 3. So this was also a behind the scene, and people actually worked out a solution for that. And this thinking process had been created. The what other behind the scene? Maybe I'll work out something which was actually from my memory, because it's more than now 20 plus years now, or nearly 18, 19 years since Chandrayaan 1 was launched actually. And I can only say that people, even in our center, were very, very unhappy because we were actually in Chandrayaan 2. This was a very bad, people were very much sort of, because you have to, as I said, that if something does not work, it's a linkage system, for, unless, if. So everything, everything, you see, space technology is not a कि आपका गाड़ी का ब्रेक एक थोड़ा फेल हो गया तो आपका गाड़ी चलेगी, ऐसा नहीं है. It is either 1 or 0. It's a binary system. Everything works or something, everything fails. It is something like that. So you can't say that, you see, partially working, even though we have in satellites what we call redundancies, and one chain fails, you can have the second working. But there are certain points which are catastrophic failures. We designate them as types of catastrophic failure, major failure, minor failure, ignorable failure, so many types of things actually. Reliability is a very important edge of everything actually. Okay, so that is there. I'll come back to him with some such incidents about Chandrayaan 1 once I recollect them.
Yeah. So Argha has a question which is not very clear. Probably he want to know whether when we will reach moon. Probably.
See, once we cross the Earth's 11.2 escape velocity, the way to go to moon is a few hours. Okay, but the time which we are at present taking, because for example, even when we were launching Chandrayaan 3, there was a Russian system with a much larger, faster payload, faster rocket actually, which decided not to take the orbital boost mechanism of Earth and take a few more days to boost it slowly. But the point was that that's a much larger rocket. So if we have that, then we can avoid that. But there is no way, there is no useful purpose served by going to moon very fast, because in space rocket, you have to actually slow down. See, you have to actually go back to again 3.3 kilometers per second. Otherwise, the moon will never capture you. You will simply go by Mars, Mangal, Surya, kahin bhi pahunch jaoge aap. तो उससे कोई फायदा नहीं है. So going, this is one big deal. You see, you can't travel so fast. If you travel fast, you need a counter rocket, counter thrusters on the reverse direction to bring the speed down. So going fast, it will require double the energy. If you go, let us say 20 kilometers per second instead of 11.2 kilometers per second, you will have to again bring 17 kilometers per second down. So you need that much fuel. So this understanding has to be there. Wow, it's like if you are driving on ice, how do you brake your car? Okay. So like the lady asked earlier, microgravity. So because there is no gravity over there is nothing to stop you. You are in free space.
Yeah. And we have our last question from Saurabh. He want to know about some of the ambitious future projects from ISRO.
There are several ambitious projects, so I request you to just see the ISRO website where there is actual what you call factual information is available. But obviously, one good thing is the heavy rocket, what we call the very heavy rocket of 30 tons type of capacity is being announced now. I was initially told it was going to carry some 70 tons. Somebody had said more than that. But there is one thing about this that you have to know that the actual Saturn V rocket of 1969 could carry more than 100 tons. So somehow the rocket technology actually in between, once we stopped the entire human race, for example, stopped going to moon in crewed orbits, what is called the human crewed orbits, human crewed missions, the requirement for such heavy rockets came down. That was one thing. So again, people are going to more rockets, larger rockets again and again, and at a single launch. So there is a thought of people think that, for example, instead of putting two payloads in one rocket and then supposingly the rocket does not work, then you lose everything. So then people, whether it's a overall, let me say that at a regular level or at a commercial level or at a continuous project level, it could be a cost benefit analysis that whether large rockets are required. So that is one project. There are plans to go to Venus. There are plans to again take another Chandrayaan. They have been announced. But these are all based on government policies. And there are obviously a new public, what we call partnership has been also started with some of the startups who have now quoted for satellites, which are actually of smaller sizes. And they are likely to introduce certain satellites as well. So ISRO itself has its plan to continue, keep going. And where we have already succeeded, there you have to have continuity of data sources. For example, remote sensing. Then as our insats will come to an age, so then we have to replace them. That is one thing. So it is likely that now with bigger launchers and with bigger satellite buses, what is called the I3K bus, we will have a I4K, I5K type of buses also. And such larger will be able to provide smaller antenna systems by which we can receive the data, and obviously much faster data rates through SATCOM communication itself. So these are the type of projects which will be happening. Then we have, as of today, I am not seeing anything announcement of to go to Jupiter or something like that. But long back, people had studies to go to Venus as well.
Yeah. So from Aryabhata to Chandrayaan, we have made a nice progress, and now ISRO is one of the superpower in the world, and we
Power,
are
power,
yeah,
power, power.
yeah, yeah. So we are towards the end of our live stream today. I have the last question for Devashish ji. This is the common questions many of the students ask, that what is the career option for ISRO? If one student want to join ISRO, how he can prepare or how he can go?
Okay. So here, one thing which you have to know is that ISRO, we talk slowly, but let me tell you that ISRO is also a central government department like any other government department. So like a railway recruitment, ISRO itself has its set of rules of central government recruitment. And annually they have a test actually, national level ISRO recruitment test actually. And then after qualifying through the test, you have to actually what we call, once you are a graduate engineer, they advertise for certain posts, everything. So that is regular engineering. Similarly, there are science recruitment. Similarly, there are technologist requirements. And so that is national level recruitment, which is through the regular government process. That is one thing. There are internships available through the HR department everywhere. So these internships are generally there is no what we call compensation for the internship as of today, because but if you can get an internship in ISRO and have an in-house 6 months internship, it adds so much value that if you are possibly going abroad or even asking for a job over here, your previous degree will be ignored, only the ISRO training will be seen. So that is one thing, because आप इसरो में घुसोगे वहां पे एनवायरनमेंट ही अलग है. आपको क्या कहते हैं कि आप जो सोचते हो वो होगा नहीं, जो होता है वो आप सोचने लगोगे, बराबर है. सो उसके जैसा एनवायरनमेंट, इट्स अ डिफरेंट वर्ल्ड ऑल टुगेदर. एंड there are several people, I have been to abroad also, they have even told me that how even you people are enigma, how even in a country called India you can even make satellites and rockets actually. So the world outside thinks differently, but the fact remains that we Indians can actually do it. So getting into ISRO, but there is one thing which I want to tell you. ISRO job does not give the perks of, let us say, certain cadre officers which other government of India does. But however, it's considered highly satisfying that you work for the country. So I have worked nearly 38 years from 1983 onwards, and I don't feel anything wrong doing it actually. So, and second thing is that thrill of seeing what you did work. So job in ISRO is slightly different from other jobs. Let me tell you that. There are engineers everywhere. Any civil construction you are doing, it's an engineering job. Any railway job chala rahe, it's an engineering job. But ISRO mein तो है, you have to actually create the box yourself. You have to design yourself. Nobody will come and give you, आप टेंडर करके कुछ नहीं मिलेगा आपको. So you have to design, development, validation, verification, prototyping, qualification, and then finally you have to carry it forward to launch. And then after launching, you may not be even sure that whether it will work or not, because so many risks are there. So, and you may have to full rework everything after that. So this is the variety of space technology challenge actually, and reliability is the keyword everywhere. So recruitment in ISRO in general is through pure government processes, through advertisement. However, there is another option of employment in ISRO, and that is through ISRO has a large number of contract employees as well. So these what we call contract jobs, they are not necessarily the lower level jobs. Engineers are also taken on contract by all the centers of ISRO, but they are through the local what we call contract agencies. There are set number of rules for them, and any Indian person can apply for it. And there is a no for that examination or something like that based on the requirement. Everything salaries are lower, but however, those engineers, I had done a lot of work on that. Maybe the guy who did it was also me. How to recruit engineers into ISRO using conveniences of labor laws, everything like that. So once you get into it, work about 2 to 3 years in ISRO, and then those who have left, there are some of the fellows who had worked with me, and I know them, who worked at Space Application Center, who worked at URSC. They have all gone to $1 lakh plus jobs abroad, because that's a different type of technology level altogether. Even within India, they have got something which they could have even never dreamed of. So there are several other options also, and the number of contract engineers in all the centers of ISRO is not necessarily small anymore. So these are the options available. But regular employment in ISRO is the only way out, is to go through the entire rigor of government job application. And now, luckily, like all other even textbooks of ISRO, what we call those MCQ, they are available. So people can go through them. The previous year's papers are also available. So, and I understand that gate qualification with BTech is one of the minimum for graduate engineers, but similarly, diploma, technicians, all recruitments are there.
Yes.
We can take a few more questions. No problem. We can take any other question is there from the audience. We can take it.
Yeah, there's no more questions, sir. So probably we can now close. So we
Okay.
are all proud about ISRO, and ISRO has achieved a lot, and we thank Devashish sir for giving us a detailed information about the working of ISRO. We are really thankful, and I am sure that the students will learn a lot from the session, and we hope that soon we will have another session from Devashish ji about Mangalyaan mission. Uh, so
Yeah.
today, today, thanks to for the audience also for your patience, and I hope that especially students, you have learned a lot, and I wish a good future for you, and I hope that this learning will help you in your career. Uh, Thanks a lot. Bye to them.
Thank you so much. Thank you so much. Yes. Thank you so much. Namaskar.